Black holes are the most extreme objects ever discovered, where gravity overwhelms space, time, and reality. Black holes are not just massive objects floating in space, they are regions where the laws of physics are pushed to their absolute limits. Predicted by Einstein's theory of general relativity and later confirmed by observation, black holes challenge our understanding of gravity, matter, and time itself. They are invisible by nature, yet their influence shapes galaxies, bends light, and alters the flow of time. Studying black holes forces scientists to confront the deepest questions about the universe. How does gravity truly work? What happens to matter at infinite density? And where does reality itself break down? Most black holes are born from the violent deaths of massive stars, far larger than our Sun. Throughout a star's life, nuclear fusion in its core creates outward pressure that balances gravity. But when the star exhausts its fuel, this balance collapses. The core contracts rapidly, triggering a catastrophic supernova explosion that ejects the star's outer layers. If the remaining core is massive enough, typically more than 3 times the mass of the Sun, gravity compresses it beyond the point where any known force can resist. The result is a black hole, formed in a fraction of a second. The event horizon is the point of no return surrounding a black hole. It is not a physical surface, but a mathematical boundary where escape velocity equals the speed of light. Once anything, matter, energy, or even light, crosses this boundary, it can never return to the outside. To a distant observer, objects falling toward the event horizon appear to slow down and fade, never quite crossing it. To the falling object itself, however, the crossing happens in finite time, with no dramatic warning at the boundary. One of the most mind-bending effects of black holes is extreme time dilation. According to relativity, gravity slows time, and near a black hole this effect becomes profound. A clock near the event horizon ticks far more slowly compared to one far away. In theory, an astronaut hovering near the horizon could experience minutes while decades pass in the outside universe. This effect has been confirmed on smaller scales using satellites and atomic clocks, making black holes a natural laboratory for testing Einstein's theories. As an object approaches a black hole, gravity becomes increasingly uneven. The side closer to the black hole experiences far stronger gravitational pull than the far side. This difference, known as tidal forces, stretches the object lengthwise while compressing it sideways. The result is a process scientists dramatically call spaghettification. For stellar mass black holes, this stretching would occur well before reaching the event horizon, tearing atoms apart. For supermassive black holes, the process may begin much later, allowing objects to cross the horizon intact, at least temporarily. Once inside the event horizon, the structure of spacetime itself changes. All possible paths forward lead inevitably toward the center. Just as you cannot stop time from moving forward, you cannot stop moving inward toward the singularity. No force, no engine, and no known physical process can reverse this motion. Communication with the outside universe becomes impossible, as even light cannot travel outward. Inside the horizon, cause and effect take on unfamiliar meanings. At the heart of a black hole lies the singularity, a point where density becomes infinite and spacetime curvature is extreme. Here, all known physical laws collapse. General relativity predicts the singularity, but it cannot fully describe it. Quantum mechanics, which governs subatomic particles, also fails under these conditions. The singularity represents a gap in human knowledge, a place where a future theory of quantum gravity is required to explain what truly happens. One of the most famous problems in modern physics is the black hole information paradox. Quantum theory states that information can never be destroyed, yet black holes seem to erase all details of anything that falls into them. If a black hole evaporates completely, where does that information go? This contradiction has led to decades of debate, involving concepts such as holography, information stored on the event horizon, and even alternate realities. The paradox remains unresolved and continues to drive cutting-edge theoretical research. In 1974, physicist Stephen Hawking proposed that black holes are not truly black. Due to quantum effects near the event horizon, black holes emit tiny amounts of energy known as Hawking radiation. Over unimaginably long timescales, this radiation causes black holes to lose mass and eventually evaporate completely. For stellar and supermassive black holes, this process would take far longer than the current age of the universe, but it suggests that black holes are not eternal. Speculative theories propose that black holes might connect to other regions of space-time, such as wormholes or even other universes. While these ideas arise naturally in some mathematical solutions to Einstein's equations, there is no experimental evidence that such gateways exist. Most physicists view these concepts as theoretical tours, rather than realistic possibilities. Still, they highlight how black holes push science toward the boundary between established physics and speculation. Because black holes emit no light, scientists observe them indirectly. They detect the intense radiation from superheated matter spiraling into them, known as an accretion disk. Black holes can also be identified by their gravitational influence on nearby stars and gas. In 2015, gravitation waves from merging black holes were detected for the first time, confirming a major prediction of relativity. In 2019, humanity captured the first image of a black hole shadow, providing direct visual evidence of these cosmic giants. Black holes are more than astronomical objects, as they are cosmic laboratories that test the limits of physics, mathematics, and human understanding. They challenge our concepts of space, time, and reality itself. Every discovery raises deeper questions, reminding us how much remains unknown about the universe. As technology advances and theories evolve, black holes will continue to guide humanity toward a more complete understanding of the cosmos, and perhaps toward answers to questions we have not yet learned how to ask.